Okay, guys, welcome back to our review of the material covering Chapter 11 and Chapter 12. This is the second problem. Let's put a number up here. Let's say number 2. And this is projectile motion and the radius of curvature. So in this problem, we are asked to, we're given this situation, they're throwing the ball through a tire. Let's here. And it is attached to something. And there's an unknown velocity. They're throwing the ball at 3 degrees from the horizontal, 6 meters downfield, and there's a tire sweep. We're asked to find the range of initial velocities that will go through the tire and the radius of curvature when the ball goes through the middle of the tire. So what we know about projectile motion is that we have this equation, right? And it's going to be either for x or y. And so we have, let's see, there's a time component right there. Initial velocity. So the position is s equals s naught plus v naught t plus 1/2 at squared. If we solve this for the y direction, then we're going to have, we know the initial and final y. So we got these. We do not know the initial velocity. We do not know time, but we do know gravity, the acceleration. Anyway, that's gravity. So it looks like we're going to need to use the x and y components. So first things first, let's see, so solution. Let's notice that the, since we're breaking it into x and y components, that we need, let's say, v naught equals v naught x plus v naught y, and v naught x is v naught times the cosine of 3 degrees, and v naught y is v naught times the sine of 3 degrees. Okay, cool. So we know we're going to start with, or we know we're going to need x to find t. So let's start with x. So we'll just say the x direction. Okay, so instead of s, I'm just going to use x because why not? So x equals x naught plus v naught x, little x, t, plus the acceleration component, but it's x direction, so I'm just going to leave that off because it's 0. The initial starting position is also 0 because we're going from 0 to 6. But we have 6, so we have 6 equals, we don't know v naught x, but we do know that it's this. So v naught times the cosine of 3 times t. We're going to need t, so we solve for t. And we say that t is equal to 6 over v naught cosine 3. Okay, cool. I bet we're going to substitute that in later on. Let's find out. In the y direction, same thing. We start with this governing equation. We say y equals y naught plus v naught y this time plus 1/2 at squared. All right, and now we can substitute a bunch of stuff in, and hopefully all that we'll be solving for is v naught. So let's say y, this is the final y, and we're looking at a range, so we'll leave that alone for now, and then at the end, once we have the relation, then we'll solve it based on the y values that we want. Y naught is 1.5, so let's see, y equals 1.5 plus v naught y is v naught sine 3, so v naught sine 3, t is this, so we'll say v naught cosine 3 over 6. 1/2 a is minus, so minus 4.905. and then t squared. So same thing, v naught cosine 3, 6, and this time it's squared. So it looks like we're going to simplify, that's fine. So y equals 1.5 plus, now here, the v naughts cancel, okay? And so we get what, 6 tan 3? So 6 tan 3 minus, square of 6 is 36, so 36 times 4.905 over, and what I'm going to do is I'm going to sort out the numbers, right? So this is v naught squared cosine squared 3. So v naught squared cosine squared 3, right? And looks like that's it. And let's just handle the numbers, right? So we can group this is plus, right? So group this together, and that is, see, I did this problem just a few minutes ago. So this is 1.814. And I will get this together. So when we rewrite it, we get y equals 1.814 minus 77.065 over, that's 5, over cosine, or excuse me, over v naught squared. Okay. And we can rearrange this so that we have v naught on the side of interest and y is in the equation. So we'll subtract, actually we can shortcut that and just do that. So we have this term right here, and we want to basically exchange places with v naught. So what we end up with is v naught equals square root of 177.065 divided by 1.814 minus y. So the direction changes because this, sorry, this is a negative sign. This, we can send that over and then just reverses that. So this is our relation. And we solve this for 3 cases, right? So y min is equal to 0.25 meters. Okay. Just try a line here to keep this organized. And when we put that value in here, we get v naught, and I'm just going to say v naught min is equal to 10.64 meters per second. Y max is 0.72 plus 0.25, that is 0.97 meters, 0.97 meters. And that corresponds, so we put the 97 in here, and that returns v naught max, which is 14.484 meters per second. So the y mid, right? So right in the middle, because so we want the range, right? So the range is going to be the between these 2 values. So the way we would write this is we would say 10.64 is less than or equal to v naught is less than or equal to 14.48. You could leave off the 4 if you wanted, but I'll just leave it there. Meters per second. You'd want the units over here as well, but this is your answer for part A. For B, we want the mid. So the mid is what is 0.61 meters. That corresponds to V naught mid, which is 12.37. And I've ran these through the thing. So for B, I guess we could say B right here, right? And just draw a line. Okay, so we have our V naught, and the equation is the acceleration in the normal direction times, or equals, V squared over rho. We're looking for rho. So here we have rho is equal to V naught squared over acceleration in the normal direction. Well, if we assume a constant velocity, a relatively constant velocity, right? We're going 6 meters. This is 13 meters per second. It's going to be pretty constant. And we assume that we're taking this at the top of the arc, then the normal acceleration is gravity, right? So this is just 12.387 squared over 9.81. So rho equals, can we still see that? Yeah, so rho equals 15.641 meters. And that's how you solve that kind of problem. Sweet, that's not too bad. I have complete faith that you guys can handle that on your own, and I will see you in the next video.